Hello everyone, my name is Nidhi Chauhan. I'm a professor at Vihar School of Pharmacy. That is a part of the Suresh Vihar University chapter. So today we are going to discuss this carboxylic acid. This carboxylic acid comes in your pharmaceutical organic chemistry first, in your second semester, in your first year. So in this topic of this carboxylic acid, we are going to study about the learning objective of this topic is that we are going to study about the carboxylic acid, and also we are going to learn about the physical properties of carboxylic acid and what is the acidity of carboxylic acid, and if a substituent is attached or bonded to the carboxylic acid, then what will be the effect of it, this substituent that is attached on this carboxylic acid. So here we are going to study these are the learning objective of this topic, carboxylic acid, and the student outcome is that here they are going to know about what is carboxylic acid, um, what are the properties of carboxylic acid, that is your solubility, hydrogen bonding, physical state. These carboxylic acids are soluble in water or not, if they are soluble in aqueous solvent or they are soluble in non-aqueous solvent, if what is the hydrogen bonding of this carboxylic acid, and what is the state of this physical state of this carboxylic. Now also we are going to learn about the acidity. What is the acidity of carboxylic acid and what are the effects of substituent on carboxylic acid? Means here we are going to study about the acidity, how the acidity of carboxylic acid can be calculated, and what are the pH of this carboxylic acid, how much it is acidic than the other compounds. So here we are going to study all these things. Uh, let's start our topic. Carboxylic acid. So carboxylic acids are organic compounds that are containing carboxylic group, that is your COOH, wherein the carbohydroxyl group OH is directly attached to the carbonyl CO group. So in the aldehyde and ketone, we have already studied that the CO is the carbonyl part, and in this carboxylic acid, the CO group is attached to the hydroxyl group, and then the full combination becomes a carboxylic acid. That is why this carbo in the carboxylic acids, this the name carboxylic acid uh, is um, is made up of both hydroxyl as well as carbonyl. So in this, you can see from the carbonyl part, the carbo is taken in this carboxylic, and in this hydroxyl, from this hydroxyl, its oxyl is taken from this hydroxyl group. So that is why from the mixture of this carbonyl and hydroxyl, the name carboxylic acid has been become. So here carboxylic acids, these are the organic compounds, means they are the organic compounds which are carrying carbon as well as hydrogen. So these are the organic compounds that are containing the carboxylic group, that is your COOH. And in this COOH, there is a hydroxyl group that is directly attached to the carbonyl group. Sorry. So here in the figure, you can see that carboxylic group is it can be represented by these three structures, as you can see the three representation of the carboxylic acid. So the carboxylic group is RCOOH or RCOOH or RCO2H. So these are the three structures of this carboxylic group. So here you can see that we can use these structures if you want to use the short form of this carboxylic group. Then you can see CO2H you can write also, and COOH. And if we have to show the double bonds in the single bonds, then we can write the COOOH. So this is the carboxyl group, or the carboxyl functional group. And if this is attached to any molecule or the alkyl group, then there is a oic acid is attached on the as a suffix is attached to this name of this name. So here the carboxylic acids are organic compounds that are containing the carboxyl group. So wherein the hydroxyl group is directly attached to the carbonyl COO group, and carboxylic group can be represented by these structures, that is your RCOOH or RCOOH, or you can write RCOOH. These are the three representations of the carboxylic acid. Next, natural carboxylic acid means if these carboxylic acids are also present naturally, we can also obtain these carboxylic acids. So these great many carboxylic acids are encountered in nature, mostly in fruits. Means in fruits, these carboxylic acids are present in nature, and these carboxylic acids were among the first class of organic compounds to be ever isolated from nature. Means these were the first class of organic compound which were isolated from the nature. That is why we know that these carboxylic acids are present in nature. So you have two carboxylic acids are known. That first is the lactic acid, and its formula is CH3CH OHCOO2H, and its name is lactic acid, and it is present in your soy milk. Means the milk that is your soy, in that this lactic acid is present, and lactic acid is type of a carboxylic acid. So this is present in naturally we can obtain, we can isolate it from this soy milk. Secondly, it is your lemon. So from the lemon, in the lemon, as we know that the citric acid is present, and citric acid is a type of carboxylic acid. As you can see, the three carboxylic acids are attached to it. Three function groups of carboxylic acid are attached in the citric acid. So this from this lemon, the citric acid is isolated, and this is the type of your carboxylic acid. So these two are the example of the natural carboxylic acid that are obtained from the nature or isolated from the nature. So edible carboxylic acid found in citrus fruit and fermented milk generally have sharp flavors. So these both of them have a sharp flavor in them. So these are the edible carboxylic acids. So we can eat it. So these are the edible carboxylic acid that are found in citrus fruits and the fermented milk, and these are having a sharp flavor in them. So the two carboxylic acids that are encountered in nature are the lactic acid and the citric acid. Many more are also present in the nature, but we have shown here the two examples that are the carboxylic acid that we can isolate it from the nature and that are present in the nature. So now the physical properties of this carboxylic acid. So what is the physical properties of this carboxylic acid? So first is the physical state. So in the physical state, we know that the lower members, that is your C1, C3, are colorless liquids and having pungent smell, and the C4 to C9 members are colorless oily liquids that are having an odor like goat butter, and the higher members are colorless, odorless, waxy solids. So in the physical state, these carboxylic acids are present. The lower member of this carboxylic acid, these are present as a colorless liquid, and they are having a very pungent smell. But the C4 to C9 member of this carboxylic acid, they are colorless oily liquids, and they are having an odor like goat butter. So the goat butter odor the order that is present in the goat butter. Similarly, in the C to C4 to C9 members of this carboxylic acid are having the same order. So these are the colorless oily liquids. So from C1 to C3, C9, from C1 to C3, they are the colorless liquids. They are having pungent smell, but the C4 to C9 members are your colorless oily liquid. These are the oily liquids. They are only the liquids. These are the oily liquids, and they are having a order like a goat or butter. And the higher member above your C10 onwards, these are colorless, odorless, and waxy solids. So these are present as a waxy solids, and these are odorless, and these are colorless. So in the physical state, uh, as you can see here, in the physical state, the lower members from C1 to C3 are colorless, but they are liquid and they were pungent smell. But the C4 to C9, they are colorless but having a oily liquid, but they are oily liquid and they have an odor like goat butter. But the higher members from C10 onwards are your colorless, odorless, and waxy solids. Means here all the members of this carboxylic acid are colorless, but the smaller ones are your liquids, but the higher members are your solids, waxy solids. Next is your hydrogen bonding. The intermolecular hydrogen bonding occur in carboxylic acid. Means the molecule of carboxylic acid, if the two molecules of carboxylic acid are present, then they will forming a bonding, they are forming a hydrogen bonding between them only. Means intermolecule, they are forming a hydrogen bonding. So the intermolecular hydrogen bonding occur in carboxylic acid, and the two molecules of carboxylic acid are associated by hydrogen bonding into dimers, that is your pair of molecules in liquid state or gaseous state, and the boiling point and solubility of carboxylic acid are associated with hydrogen bonding. So here in the hydrogen bonding, the intermolecular hydrogen bonding occurs in carboxylic acid. So the carboxylic acids are having a hydrogen bonding intermolecules, and the two molecules are associated by hydrogen bonding, and they forms a dimer. They forms a dimer, means they are forming a pair of molecules in your liquid state or in your gaseous state. In liquid as well as in gaseous state, they are forming a dimer, and they are forming a dimer of hydrogen bonding in this carboxylic acid. And the boiling point and solubility of carboxylic acids are associated with hydrogen bonding. So these boiling point and solubility of this carboxylic acid are associated with the hydrogen bonding. Means here the solubility and the boiling point are associated with the hydrogen bonding. If there is no hydrogen bonding, then what will be the boiling point and what will be the solubility? And if there is a hydrogen bonding, then what will be the boiling point and the solubility of this carboxylic acid? So here the intermolecule, you can see in this picture that there are two molecules of this carboxylic acid, and they are forming a hydrogen bonding, and they are forming an intermolecular hydrogen bonding. So here intermolecular hydrogen bonding is occurring between the two molecules of this carboxylic acid, and the two molecules of carboxylic acid. You can see here hydrogen bonding is occurring. Hydrogen, this is the one molecule and this is the another molecule. So the hydrogen from this alcohol part is getting attached, forming a bond with this oxygen of the another molecule, and the hydrogen of this molecule is getting bonded to this oxygen of the another molecule. So there is a hydrogen bonding between the two molecules. There is a hydrogen bonding between the two molecules of this, and the intermolecular hydrogen bonding is occurring in carboxylic acid, And two molecules of carboxylic acid are associated by hydrogen bonding into dimers. So they are forming a dimer. Two molecules in di means two dimers, a pair of molecules they are forming. And in a liquid state or in gaseous state. But in case of liquid as well as in the gaseous phase, they are forming a hydrogen bonding. And the boiling point and solubility are dependent on this hydrogen bond. So first, it was your physical state. In the physical state, the lower members means from C1 to C3. They are present in the form of your colorless liquid at having a pungent smell. In case of your C4 to C9 members, are your colorless liquid, colorless oily liquids, and they are having an odor like your food butter. Thirdly, it is your seated members, means your higher members, and these are colorless, odorless, and having a no odor. Colorless, odorless, and these are Dixie solid. So these are present in the form of solid, and that the lower members are present in the form of liquids. But all the carboxylic acids are colorless. And the hydrogen bonding in this, the two molecules of this carboxylic acids are forming a colorless, a hydrogen bonding means they are forming an intermolecule. Between the molecules, they are forming a hydrogen bonding, and they are forming a dimers, which means they are forming a pair of molecules in the liquid or in the gaseous state. So the boiling point and the solubility of carboxylic acid are dependent on hydrogen bonding. So this boiling point and solubility of this carboxylic acids are associated with this hydrogen bonding. Next is your boiling point. Carboxylic acids have higher boiling points than the organic compounds like your alcohols, ethers, aldehydes, or ketones of similar molecular weight. For example, here given acetic acid has higher boiling point, that is your 118 degrees centigrade than the propanol, although the two have the same molecular weight. So it means here the carboxylic acids are having higher boiling point than the organic compounds like your alcohol, ethers, aldehydes, and ketones of similar molecular weight. These are carboxylic acid and these alcohol molecules. These are having the same molecular weight, but due to their same molecular weight, in case the carboxylic acid is having a higher boiling point than these organic compounds because of the hydrogen bonding. So for example, here given that acetic acid is having a higher boiling point. Means the acetic acid, which is your carboxylic acid, it is having a higher boiling point, that is your 118 degrees centigrade. Then the one propanol. Propanol is your alcohol, and it is having less boiling point than this lower boiling point than this carboxylic acid, acetic acid boiling point. So although the two have similar molecular weight, but both of them, this one propanol and this acetic acid, both are having the same molecular weight, that is your 60.1. But then also this acetic acid is having the higher boiling point than this alcohol, which is your one propanol. So similarly, the butanoic acid and one pentanol have similar molecular weight, but the boiling point of butanoic acid is 163 degrees centigrade, is more than that of one pentanol. So similarly, this butanoic acid is a carboxylic acid, and one pentanol is your acetic acid, and this one pentanol is your alcohol, and this alcohol and carboxylic acid both are having the same molecular weight, that is your 88.1, and but the boiling point of sorry but the boiling point of this butanoic acid, that is your 163 degrees centigrade, is much more than the one pentanol. So it is having 137 degrees centigrade, and butanoic acid is having 163 degrees centigrade. But they are having the same molecular weight, that is your 88.1. burning. Now, why the carboxylic acid is having a higher boiling point than these alcohol, ethers, aldehyde, or ketone, but they all are having the similar molecular weight because the two molecules of a carboxylic acid form two hydrogen bonds with each other, while two alcohol molecules can only form one hydrogen bond. So here, in this case, you can see, I have already told you in the last slide that the carboxylic acids are forming an intermolecular hydrogen bonding, and they are forming a dimer, that is your pair of molecules is forming. That is why this carboxylic acid uh, is having a high boiling point as compared to the alcohol, because these two alcohol are forming only one hydrogen bonding, and this carboxylic acid is forming two hydrogen bonding. So the boiling point of carboxylic acid increases with increases in weight, molecular weight. So the boiling point of this carboxylic acid increases as there is an increase in the molecular weight. So the boiling point. So the third point is physical property of this is boiling point. So the boiling point means carboxylic acid. So the carboxylic acid is having carboxylic acids have higher boiling points than the alkyl compounds like your alcohol, ethers, aldehydes, or ketones of similar molecular weight. These all are having a similar molecular weight, but the carboxylic acid is having the higher boiling point. For example, is your acetic acid. For example, is your acetic acid that is having a higher boiling point and then the 1 propionol. Acetic acid is having 118 degree centigrade and the propionol is having 97. But both of them are having the same molecular weight, that is your 60.1. Similarly, the butanoic acid and 1-pentanol, are having the similar molecular weight, but they are having different boiling point. Butanoic acid is having higher boiling point, that is the 163 centigrade, and 1-pentanol is having a less boiling point, that is your 137 centigrade. Because the two molecules of a carboxylic acid form two hydrogen bonds with each other, while two alcohol molecules can only form one hydrogen bond, and the boiling point of carboxylic acid increase with increase in boiling point. Because here you know that the carboxylic acids are forming, the two molecules of this carboxylic acids are forming the two hydrogen bonding with each other. That is why it is your intermolecular hydrogen bonding. But the two alcohol molecules are forming only one hydrogen bond. So the boiling point of carboxylic acid increases with the increase in your molecular weight. Next is your solubility. Now the C1 to C4 members are more soluble in water. The C1 to C4 members are more soluble in water. This is due to the ability of the COOH group to form hydrogen bond with water molecules. So due to strong hydrogen bonding, carboxylic acids are more soluble in water than alcohol, ethers, aldehydes, or ketones of comparable molecular weight. So the solubility of a carboxylic acid in water decreases as the molecular weight of carboxylic acid increases. So here the C1 to C4 members are more soluble, in water, and this is due to the COOH group. This is due to the COOH group that forms hydrogen bonding. This is due to the ability of the COOH group that form hydrogen bond with water molecule, and due to the strong hydrogen bonding, carboxylic acid, these carboxylic acids are having the more solubility in water as compared to the alcohol, ethers, aldehydes of ketone of comparable molecular weight. So in this case, you will see that C1 and C4 members means from the carbon 1 to your carbon 4 member, these are more soluble in water. Their solubility is more in water, and this is due to the it is because of having the soluble this having the COOH, which forms a hydrogen bonding with the water molecule. So this is forming this carboxylic acid are forming hydrogen bonding with the water molecule, and due to the strong hydrogen bonding, because here if they are forming a hydrogen bonding with the water molecule, then this hydrogen bonding is very strong, and due to this the carboxylic acid are more soluble. These are more soluble in water, and more soluble in water than your alcohols, ethers, aldehydes, or ketones, and of comparable molecular weights. Means if the two different, means one is a carboxylic and the other is a alcohol, and both are we have to make them soluble in water. Then the carboxylic acid is more soluble in water as compared to the alcohol, and both of them are having the same molecular weight. Then also the carboxylic acids are having more solubility than in water than other compounds. The solubility of a carboxylic acid in water decreases as the molecular weight of carboxylic acid increases. So this solubility of this carboxylic acid in water is decreasing as the molecular weight of carboxylic acid increases. Means why this is decreases? Because there is a addition of the alkyl group to this carboxylic acid. That is why as the higher members, as the higher members, higher member it will be of this carboxylic, or the molecular weight of this carboxylic increases, then the solubility is decreasing. And this is due to the carboxylic acid consists two different polarities, because it is having the two different polarities, a polar hydrophilic carbonyl group and a non-polar hydrophobic hydrocarbon chain. Similarly, which I have told you, that they are having the hydrophobic hydrocarbon chain, means they are having the alkyl group that is attached to this carboxylic acid. So they are having the two different polarity. One is your polar hydrophilic carbonyl group, means the carbonyl group is your polar and it is hydrophilic, means it can be dissolved in water. But secondly, it is also having a non-polar hydrophobic hydrocarbon chain, means the R that is attached to this carboxylic acid functional group, that is your hydrophobic, and that R is a chain of the hydrocarbon in case of higher member of this carboxylic acid. So here the carboxylic, the hydrophilic carbonyl group increases water solubility, whereas hydrophobic hydrocarbon chain decreases water solubility. So the hydrophilic carbonyl group, the hydrophilic carbonyl group that is present in the carboxylic acid, that is increasing the water solubility, but the hydrophobic hydrocarbon chain, the hydrophobic hydrocarbon chain that is attached to this carbonyl group, that is decreasing this water solubility. Therefore, C5 members are partially soluble and the higher carbon chain members are insoluble in water, but readily soluble in this organic solvents. So the C5 members, from C1 to C4, the solubility is good, but from the C5 members, but the C5 member, we are talking about the C5 member. C5 member are partially soluble. I means partly soluble. They are not fully soluble. So and the higher carbon chain members, Means now the higher members of this carboxylic acid, these are insoluble. These are insoluble in water because more hydrophobic hydrocarbon chain is present in them. So and but they are soluble in your ethanol, ethers, and your benzene. Once again, that the solubility first was your physical state, second is your second, what was the second? Second is your hydrogen bonding, third is your boiling point, and fourth is your solubility. So the C1 and C4 members are more soluble in water, and this is due to the ability of the COOH group to form hydrogen bond with water molecules, and due to strong hydrogen bonding, carboxylic acids are more soluble in water than alcohols, ethers, aldehydes, or ketones of comparable molecular weight, and the solubility of this carboxylic acid in water decreases as the molecular weight of carboxylic acid increases, and this is due to a carboxylic acid. This is due to the carboxylic acid consists of two different polarity, a polar hydrophilic carbonyl group and a non-polar hydrophobic hydrocarbon chain. The hydrophilic carbonyl group increases water solubility, whereas hydrophobic hydrocarbon chain decreases water solubility. Therefore, C5 members are partly soluble and the higher carbon chain members are insoluble in water, but readily soluble in ethanol, ethers, and your benzene. These are the physical properties. Now, the acidity of carboxylic acid and effect of substituent on acid strength. So here, what is the acidity of carboxylic acid and how we can detect it? The carboxylic acid can ionize in water into carboxylate ion and hydronium ion. As you can see here, RCOOH. When this carboxylic acid is present in water, then it is ionizing this, and there is a formation of carboxylate ion and the hydronium ion. Hydronium ion is the H3O plus, and the carboxylic acid is ionizing the water molecule, and there is a formation of this carboxylate ion and a hydronium ion. And the equilibrium constant K for a given equation can be expressed as K equals to RCOO negative hydronium ion upon this first equation, that is the first part, RCOOH and H2O. Since water is in excess, then KH2O equals to Ka, and the above equation can be written as this Ka equals to RCOO negative and hydrogen ion upon RCOOH. So Ka is known as acid dissociation constant, and which is a measure of acid strength of an acid, and the pK of an acid is negative logarithm of Ka, and commonly used parameter to measure the acid strength of an acid. The low value of pKa corresponds to more acidity, and high value relates to less acidity of acid. So this pKa equals to minus log Ka, or you can say pKa is inversely proportional to this log Ka. So the acidity of this carboxylic acid can be found out by the carboxylic acid, which can ionize in water into carboxylate ion and hydronium ion as RCOOH plus H2O, and this RCOO negative plus as H3O positive. This is the carboxylate ion, and this is the hydronium ion, and the equilibrium constant K of a given equation can be expressed as your K equals to your this second part RCOO negative, that is the carboxylic ion, and your hydronium ion upon your carboxylic acid upon water molecule. Since water is in excess, since that means here water is in excess amount. Therefore, KH2O equals to your Ka. Hence, the above equation can be written as Ka equals to your carboxylic ion and hydronium ion upon carboxylic acid. So this Ka is the acid dissociation constant, and it from this Ka we can measure the acid strength of an acid. So this the pKa of an acid, that pKa of an acid is a negative logarithm of Ka, or we can say that pKa is inversely proportional to this Ka, log Ka, and commonly used parameter to measure the acid strength of an acid. This is also a parameter from which we can measure the acid strength of an acid. Sorry. So the low value of pKa correspond to more acidity. If the value of this pK is less, then it means that the acidity of the acid is more. And if the value of this pK is high, then this the acidity of the carboxylic acid is low, means less. So this from this pK we can measure our acid strength of an acid. If this pK, if the Ka value is high, the pK value is high, then pK is less. So this is the inversely proportional to each other. So from pK, if pK value is high, then the carboxylic acid acidity is low or less, and if the pK value is less, then the acidity of the acid is more. For example, here given that the acetic acid is dissociated as, it means the acetic acid is ionizing the water in the form of this CH3COOH, that is your acetic acid plus water, and this is your acetate ion plus hydronium ion, and the acid dissociation constant Ka for a given equation can be expressed as like this. So the pK value equals to 4.76. So the value of pK for aliphatic carboxylic acid are in the range of 4, between this 4 to 5. Therefore, the carboxylic acids are weak acid, and their acidic strength decreases with increases in molecular weight. If the molecular weight is increasing, if the molecular weight of the carboxylic acid is increases, then there is a decrease of the acidic strength of this carboxylic acid, and that is why the carboxylic acids are your weak acids. These are the weak acids that are this carboxylic acid. So from this acetic acid, which is a aliphatic carboxylic acid, it is dissociated into acetate ion and hydronium ion in the presence of water, and the acid dissociation constant, that is your Ka, for a given equation can be expressed as your Ka equals to acetate ion and hydronium ion upon acetic acid equals to 1.74 into 10 raised to power minus 5, and the pK equals to 4.76. So its value pK equals to 4.76. So its value is, so the pK of the aliphatic carboxylic acid are in the range between 4 to 5. Therefore, carboxylic acids are weak acid, and their acidic strength decreases with increases in molecular weight. If the molecular weight of the carboxylic acids are increasing, then there is a decrease in the acidity of the carboxylic acid. So this is the acidity of the carboxylic acid. Next, these are some of the values of simple carboxylic acid, and here that HCaOOH is a methanoic acid, or you can say a formic acid in the common system according to common system, and its pK value is a 3.75. It is more acidic than other acidic acid. So here CH3COH is having the 4.74, that is the ethanoic acid. Then next is the propanoic acid. The propanoic acid is having 4.87. So now you can see here they are increasing. Their pK value is increasing because there is the attachment or there is a bonding of this hydrocarbon chain or alkyl group is attached to it. Next is the butanoic acid. It is having 4.82. Next is the pantanoic acid. It is having 4.81. Next, hexanoic acid, that is having 4.88. Next is your octanoic acid, which is having a 7-member hydrocarbon chain, and it is having a pK that is your 4.89. So they are lying between the 4 to 5. So next is the decanoic acid, that is having a 4.84. But in the case of this aromatic carboxylic acid, it is also, they are also lying between this 4 to 5. So they are having a pH that a pK that is your 4.19. And in case of taulic acid, because here CH3 group, CH3 group is an electron donating group and it is having a 4.36. But next is your para chloro this benzoic acid, that is having a 3.98, because this is a withdrawing group that is attached on the para position of the benzoic acid. That is why its pK value is 3.98. Next is a nitrobenzoic acid. So it is having a 3.41. Next, fluoro is attached to this aliphatic carboxylic acid, and it is having a fluoro is the electron withdrawing group, and it is having a pK that is your 2.59. In case of chloroethanoic acid, it is 2.86. Next is your bromoacetic acid, that is your 2.90. Next, iodoethanoic acid, that is having 3.18. Next, dichloroethanoic acid, that is having 1.26. And next is the trichloroethanoic acid, that is having 0.64. So these are all acidic strength of this carboxylic acid, and this trichloroethanoic acid is having in a pK value that is much less. It is very less as compared to the other, because here the 3 chlorine that are the electron withdrawing, they are attached to this ethanoic acid. That is why it is having a less pK value. There are two regions of acidic nature of carboxylic compound. First is the resonance effect. So you can see here that the carboxylic acids are having the resonance effect in them. So the carboxylic group shows resonance structure in which the oxygen atom of OH group contain a positive charge, which is not a stable, hence can lose bonded hydrogen atom in form of proton and convert an oxalate ion, carboxylate ion. That is the reason the equilibrium between the carboxylic group and the carboxylate ion lies towards right side. So here you can see in the resonance structure of this carboxylic group, two structures are shown here, and the resonance structure in which shows resonance structure in which the oxygen atom of OH group contain a positive charge. This OH group is having a positive charge in it, and this is not stable because here the H positive, this H positive can lose from here as a proton. It can be removed from here. Removal of this H positive can be occur from here, or bonded hydrogen atom in the form of proton, and it can convert. Then after that, after the use of this hydrogen atom from here, it can convert it into the form of carboxylate ion. And this is the reason why this carboxylic group and carboxylate ion lies towards your right side. Next, this is your carboxylate ion, an ion that is Also stabilized by resonance. This is the carboxylic, sorry, this is the carboxylic acid and ion that is stabilized. And stabilization of the anion is much greater than that of the neutral carboxylic group. And in the carboxylic anion, the CO bond are of equal length and the two carbon contributing structures have equal weight in the hydrogen. So as you can see in the lower structure of this carboxylic ion, there is a length of this, they are having the equal length. Uh, and they are having the equal weight in the structure. Next is the effect of substituent on acidity of carboxylic acid. Means if the substituent is attached to the carboxylic acid, then what will be the acidity of the carboxylic acid? So they can affect by the affecting the stability of the carboxylic anion, and a substituent that stabilizes the carboxylic anion, they promote the dissociation and result in the stronger acid. So there, if there is a substituent that is stabilizing the carboxylic anion, they are causing the dissociation, and due to which there is the formation of the stronger acid. So the substituent on the alpha carbon atoms are most effective in order to increase its acid strength, and electron withdrawing groups such as NO2, CN, etc. enhances the acid strength of the carboxylic acid due to the increase because they increases the stability of the carboxylic anion to the decolocalization of the negative charge by inductive or the resonance effect. However, the electron releasing group such as your alkyl group, they reduces the acidic strength of the carboxylic acid. So if an alkali group is attached to an carboxylic acid, then they are reducing stability or the acidic strength of the carboxylic acid because they are the electron releasing group. But if the electron withdrawing group such as your NO2 and CN, they are attached to the carboxylic acid, then they are increasing the stability of carboxylic ion, and that is why they are increasing the acidity of the carboxylic acid. Next examples are shown that nitro and the CH3 group are attached, and the nitro benzoic acid is having the more or acidic strength than as compared to this paratolic acid. So here you can see the pK is 3.41 in case of para nitrobenzoic acid, and in case of paratolic acid it is 4.36. So it is due to the fact of this nitro, that is your electron withdrawing, and the para alkyl methyl that is attached to the this benzoic acid. Similarly, phenolic acid is having a pK 4.74 because it is attached here. Attachment of alkyl group is there, and the methanoic acid is having the 3.75 because there is no electron releasing group is attached to it. Next, this is the pK strength, presence of electron withdrawing group. Nearly the carbonic group decreases the pK value, means the magnitude of the substance depends on the distance. How much distance this substance is attached to this carbonyl group. So the higher electronegative substance on the alpha carbon atom further increases the acidity of the carboxylic acid by inductive effect. So here you can see the fluoro is attached, so their pK value is 2.66, and when as compared to the acetic acid. To study the effect of multiple halogen substitution, compare the value of pK for acetic acid. So here you can see the acetic acid, means here three chlorines are attached to this carbon, and they are having the pK value which is much less as compared to the two chlorine that is attached to the pK and one chlorine that is attached to this acetic acid, and there is no chlorine or no electron withdrawing groups are attached to this is acetic acid. Next, carboxylic acids are stronger acids than alcohol, and compared to the alcohol, they are much stronger acids because of the delocalization of the negative charge of the carboxylic anion through resonance and the electron withdrawing inductive effect of the carbonyl group. What is the correct order of decreasing minus I effect? That is your D. Due to the presence of CX polar bond in alkyl halides are more reactive than corresponding alkane. Which compound is more acidic? That is your H2S, which is less acidic. That is your CH4. Acetic acid is obtained when which of the given reactions take place. that is your C. Hydrolysis of CH3, CH2, NO2 with 85% H2SO4 give the following compound: acetic acid. Arrange the following groups in the order of decreasing effect, that is your A. References. So these are the references from where we can study this topic of this carboxylic acid. And thank you so much for today's lecture.